when a new team starts, they can leverage the experience of all teams that came before them. But they are not limited by their design decisions because we do not, at least unless the team wants to, share code. They start from scratch. So when a new team starts, they think, okay, this is what the others did, this is the challenges they had, how can we make it better? And that leads to an evolution that is driven by the teams. An evolution in different dimensions. So for example, technology-wise, we started out doing PHP and MySQL in the backend. That's just 4 years ago. And now we do servers in Erlang and Scala, Akka, you name it. A huge change in what we did there. All driven by these incremental steps of a new team trying something new and adding it to the knowledge of the company. And it's the same also for architecture. We started off with very standard stateless application servers in the backend. And nowadays, the more complex games to reduce load on the database, they use a stateful approach. And the same also for platform. We started on Facebook.com, we went to Google+, went away, and are now on iOS and on Android. But there's one evolution that I want to talk about today, and that's user interaction. It's a bit like game design. How can we enable cooler games that you play together with your friends, the same game, more meaningful, and how can we enable this with technology? And again, we had some steps in the past. This is the part that I will tell about, and then I will hand over to Patrick in the second part of the talk, how we improve on that. We started out very simple, and sharing, playing together with friends was just like, you see what they did. Think of PacMan. Yeah, I hope you all played PacMan, or at least know the game. You play it, it's a really cool game, but that's not really interaction, you play it alone. The only interaction is you have a high score, and your friends try to beat your high score, and that's it. And actually, this is our latest game. It's a huge success, but technically speaking, it's not much more advanced than PacMan in this regard. You play levels, you have a score. Here I played level 145, and here what is cut down are my points and those of my friends, so I can compare how they did. And you can also see how far they progressed on the map. So here you can see that Patrick, my co-speaker, is just playing level 38 and basically sucks in the game. I'm sorry to say that. But he's not in the room, so... and technically this is very simple. I mean, this is the most simple approach. When I play, I write to my database and I write to a table which is named score or something. And then someone else comes along and reads from the table. So synchronization is easy because I write my stuff and someone else reads it. Simple. A bit more sophisticated, and that's also a very common approach that you have in many games that play in social networks like Facebook, is an inbox situation. Think of chess. You send your move, write it on a postcard, send it to someone, and that someone takes that card and applies it to its local state, his chessboard. It's a turn-based gaming. You have it in Empire Deluxe, a great game. I mean, if you have not played it, you lost something back in the 90s or 80s. And Civilization, still the same principle. When I play multiplayer, I do my turn, and then I wait while the other is doing its turn. So I put my turn into their inbox. Kingsbridge, this is a game that we have been doing, follows the same principle. When other people visit my village, they can collect taxes at my house, and it looks like this. Like here, see with the circle. So here, I think this is Nadia. She collected taxes, and I can choose to accept or refuse these things. And when I do accept, then I apply their changes. I read it from the inbox and apply it to my state. But I'm in control of my own state. And she cannot directly affect that. So it's a very simple system. Here, still again. So how does it look like? I do my client, and I write in the database. Exactly the same thing. The only difference is that another player can write directly into my state in a separate area. It's a bit like a queue, or depending on the implementation, can be a database table. So basically they push something on my queue, on my inbox, and I pop it off whenever I want to apply that change. Simple. Most games work that way in Facebook. Architecturally we evolved this a bit. The database was a big bottleneck, and we now run mostly on stateful application servers, so all the hot memory is within the application server itself. But this part about the inbox is still the same. Very often it's just a simple Redis database, because it works. I could tell you a lot more on this, how we evolved to stateful things, but this is not scope of this presentation. If you want to know more, please go to this URL, Wooga/backend, and we have plenty of presentation there on the topic of how we involved our architecture. But let's get back to user interaction. What you really wanted to have is real interaction. Someone lets something fall on the floor and I pick it up. This kind of interaction. Things like you have in the multi-user dungeon. Did any one of you ever play Mud? Yes! Take sword, go north, kill monster. Yeah, that was the good old times. Yeah, 23 years ago. I think I played the start in 1990. And The Descendant, World of Warcraft. Probably the most successful game ever. Basically, the left one is the grandfather of the right one. So this is what real interaction is about. And we did such a game. It's named Fantastic Force, and this is how it looks like. You can do lots of things there, and you can also fish. That is, if you can fish. I can't. But the nice thing is, you can also be visited by friends. So here a friend comes by, let me grab that dark set she doesn't fetch it away from me, and we fish together. So how does this work? This is working on any browser, this is working on any firewall. This is just a simple Flash game. Technically speaking, we both have our clients, both Flash clients, and we have a corresponding process within the stateful application server. This is written in Erlang, and that process holds our state and controls the connection back and forth. But there's also a shared process which administrates and holds a state for the location. In this case, the beautiful landscape we saw and the river. So when I do something, I apply a change to that location process, and the state changes. And she can be notified on that state. So it goes from the user, goes to the location, to user, and then back. And the back thing is that we have a back channel. That's the one thing. So I can be informed by the server of a change that happened to the world. And we use HTTP chunk transfer for that. That's the same thing you see when you watch a YouTube video. The client opens a socket, the server sends some bytes but does not close it and keeps sending bytes over the stream. And this works beautifully even on Internet Explorer and anything. It's much less pain than WebSockets, for example. It just works. And then you can do something like, she fishes a fish, and I pick it up. So there's a fish. I go over, and I grab the goldfish, because I'm a mean bastard, and I cannot fish, but she can. So the complex thing with these kind of games is, what if she picked the fish at the same time? Who gets it? That's the problem. So, and what we did then is basically we have an approach where the client must never wait on the server, because we expect latencies of up to 1 or 2 seconds in this kind of environment. So the client is very optimistic. So if my client thinks I can pick up the fish, it lets me pick up the fish. Then the message is sent over to the server, but maybe she was fast and already picked up the fish. That means when my user process wants to try and get up the fish in this single-threaded process, it gets, no, we can't get it, and it goes back. And then the client needs to roll back everything that happened before. And we roll back because we have, how we do it is we have a local log of everything that has been worked before. So every committed action committed by the server is put on that log, and then we roll back, basically start the whole session, we play the whole session up until that point, and then start playing again. And this is how it looks like. It actually took us 30 minutes to record this rare occasion, because it's not 2-second delay, but a lot faster. And so this is very rare, and this is how we get away with it. But it works. Very simple. This was our first step into the realm of real multiplayer. And probably with this technology you could do something like Diablo, if you wanted to. Unless you have 5,000 players, but more like 10, this works. We've also done a presentation more on like how this works in detail last year on TechMesh. Check it out if you want to. So we basically have seen that we could do real interaction, but we wanted to do real-time interaction much faster, more like shooting at each other, racing cars. We wanted to do Mario Kart or StarCraft. And that's a whole sort of different game, much more state, much more fast-paced. And the real problem behind is you have a distributed system. You have many clients out there. A minimum is 2 player clients, but maybe more depending on the game. And you have the server, and they have diverging state. It all looks a bit different because there's time synchronization. And what comes worse of is you have some players who want to cheat. They want to be on top of the others. And we have to prevent them from cheating. It's not like a distributed system that everyone cooperates, but we have some people who actually want to disrupt the gameplay by gaining advantage. So we have to avoid that. And we have the problem like, it should look good. No lag compensation, not like, oh, I spawn a Zerg in StarCraft and a second later it appears. I mean, what kind of game would be that? That would be fun. So there's plenty of information out there. So Quake World, for example, that's in the upper left corner. That's open source now. So you can look at the source code, and there's many blog posts of how they did it, and it's really cool stuff. On the right upper corner, Counter-Strike, they have a really cool wiki where they explain how they did things, especially on the network level. Age of Empires, really cool blog post. I think it's called 1,500 Archers on a 28.8 kilobit modem or something like that. And it's a really problem because they have huge state, they have thousands of units. How do you synchronize this? And Halo 2 also, there's a really awesome presentation from one of the game developers conference, how they explain how they do things. And we also played around with this, and we were pretty confident that we could build such a game. As long as we can rely on a decent throughput of the network, a low latency of the network, having not too many packet loss, and no jitter. So everything smoothly. Yeah? Cool. There was just one problem. We shifted our company focus to become a mobile company. So all games were now developed on mobile first. We do all game development for iOS first. And mobile means 3G. So before the device connects to the really fast internet, you first connect to 3G. And 3G means limited bandwidth, especially on upload. It means not so good latency. It adds roughly 100 milliseconds just on top, just because it's there. You have lots of packet loss when you move from one cell to another, or if you're in a stadium with 5,000 other people, like here probably right now. If you use 3G, have fun. And you have lots and lots of jitter. Still, we said we wanted to do that. And we do that by launching a team and letting a team build a game and then see if we can do it. So we decided to do a game that's called Bomberman. Who here knows Bomberman? Oh, I love you. So basically, multiple players on the map all move around, dropping bombs. That bombs have a countdown of a second or so, and when it explodes and it kills the player, great. The last standing player wins. And the nice thing is this 1 second countdown of a bomb. That's a really nice way to counter lag. So how did we do that? Patrick, please tell us.
Hello? Does my... Yeah. Okay. Can everybody hear me? Yeah. Excellent. So, yes, we set out to build a Bomberman style game for mobile, and we just wanted to see if we can do it because we had never done such a thing before. What you see now here is the lobby where we do the matchmaking, so that also has to be in a casual way. And so the primary goal, if you don't know it, is do not die first and then blow up things, gather up things. With those amazing power-ups. So we made the thing happen, and in my experience, it is playable up until latencies and oh, you get some replay. That's also a nice touch. So we made that possible, and I think it's still playable in my experience to latencies up to like even 400 milliseconds, which is pretty good. I will try, I think, after the talk if I can get it to work with GPRS here. We will see about that. So how did we build that? First, we did a lot of research because we had never built such a thing and we weren't sure how to do it, and there are vast resources out there, and You're trying to figure out what do we really need to do. We don't have time to invest like a year or more coming up with all those great solutions and frameworks. So we had to go quickly move on forward. And I can tell you that it is possible. So we didn't do all of these things. We just took the ones that we needed to do, and we took baby steps. So just to figure out what we're doing, what we need to change from one iteration to the next. And this is not a scientific graph. It's a very pop science graph. It just tells you that you can get a far way in multiplayer gaming without doing the super complex stuff. On the other hand, if you want to please your users, you reach a point where you have to add more complexity, but it normally happens at the end. So let's look at the first prototype that we've built from the scratch. And it had this very basic structure. You had mobile clients, a server. The clients would send move commands to the server, and the server would relay them to all the other clients and also store it internally. And the same way you would place bombs. And then the server would tell the clients that a bomb exploded. So please note that we're only sending around commands and not state. And there's no synchronization in here whatsoever for the game to resynchronize. And then the server eventually would decide on game over. So how did we build that? We used TCP for starters because it is easy and to get to, and TCP does a lot of the things as a protocol. And we just wanted to make it work quickly without dealing with UDP and the problems it brings. And we used JSON. I think it doesn't look like a very typical approach for a multiplayer game, especially if you read the literature, but it was close to us, not the simplest thing, but an easy thing to get something working. And it turns out it worked very well on Wi-Fi. Local Wi-Fi, but also over the internet if you had a really good internet connection. So to verify the concept of Bomberman, that was good enough. However, on 3G, it didn't work. It didn't work at all. And especially on our CTO's mobile phone, I call it the iPhone of doom because he gets the worst network condition at any point in time you want to have him. And one of the reasons of 3G is a problem is jitter, not only in latency but also in bandwidth. Right? So you have these constant changes in bandwidths and latencies that you will have on a mobile network. It is a shared resources. It depends on the distance from you to the cell tower, how many people are using it, which protocol are you allowed to use, have you used up all your monthly data quota, do you have to fall back on GPRS, all those things, right? Drop packets. Packet loss is a big problem. And so what does TCP do for us to help that? It is resending the messages so that drop packets get redelivered, and also it is ordering them, because in this architecture we had, order is actually very important, the order in which they arrive. Actually, there's a small problem with the order, the way the architecture is, but in general that would work out. And it would even try to optimize for bandwidth and sending rate, right? So Nagel's algorithm would go and try to optimize your bandwidth at the expense of latency, which is not really what you want to have in this kind of game. You can, by the way, turn it off with TCP no delay as a setting. And also it controls the sending rate, how fast it's going to send, so it's not going to overflow the other link. Those are very good features of TCP, but not really what we want, especially in this environment with high packet loss. So one of the fun effects that caused that is when packets would not get received by a client for a period of time. For instance, I see Jesper playing on this upper right corner, and a few seconds later, all of a sudden he warps all the way through the screen like the $1 Million Man. Then you know, okay, something got stuck along the way, right? It could get worse. On really choppy networks, it was barely playable because TCP just tried to do its connection wizardry with the result that nothing made it through. So we had to fix that problem. And if you read a lot of forums, you see, okay, UDP is the thing you need to do, real time, UDP. Okay, we wanted to try out UDP. Keeping this current infrastructure that is completely command-based, and answering the big question that I had, can we get UDP to work on 3G networks? I didn't find a lot of resources on the internet that actually says, yes, you can do it. It works. Because it also needs to work both ways, right? The client sends information to the server and the server responds also on a different port, of course, through UDP as well, and you don't know if the NAT firewalls of your data provider is supporting this or not, if it's letting it through or not, what are the firewall rules. So we didn't know. We wanted to just test it out. And to give us a sense of packet loss and to make experience in developing our own virtual protocol, we decided to implement a poor man's TCP, which is, by the way, a complete carbon copy of Glenn Fiddler's gafferongames.com description on how to build something like that. So we started adding sequence numbering so we would know the order. Sometimes we would just decide to drop them. And also a way of acknowledging with acknowledgement field, which is a 32-bit integer that uses a bit mask just to flip bits as a 1. If you have packet number 30 and the first bit is flipped, you would say, okay, you received the 30th previous packet, right? So you can't say which specific number, but just the previous 31. And since you use monotonically increasing numbers, it gives you a sense of, okay, was this package acknowledged in the last 30 messages? If it wasn't, it probably doesn't matter in that scenario. So we would that, and we would add the user ID, so this would allow us to survive network changes. Because normally what you do is you use the combination of IP address and remote port to identify a client. However, if your player is switching networks and changes its IP address, you no longer know who they are if they're in the midst of gaming. So by adding a user ID, sort of as a session ID, you know that, who the user is. And also interesting tidbit here, network order, like little endian, big endian, it matters. It cost us, I think, one morning to figure that out, because on Erlang, we were network order doing things, and the clients were doing stuff in little endian, and that causes you problems if you use integers the wrong way around. So let's look at what we did. We did ordering, yes. Acknowledge packets, yes, to a certain extent. Resending packets, no. Flow control, no. Congestion control, no. And I can tell you, it did work. So far what we tested, we tested in Germany a little bit, in the Netherlands, I tested just half an hour ago outside of the conference center, so it seemed to have worked here as well, and a few other countries. I can't speak for all switchy providers, but it generally works fairly well. However, the game itself, UDP works, the game itself, no. Not even on Wi-Fi, right? It was just unplayable. On 3G, forget about it. What was the reason? We are still at the same problem, packet loss. And if you look at the protocol that we're just sending around commands and never state, and there's no synchronization built into all the clients to come to the same concept, that everybody would see something completely different. You had inconsistent state all over the place. So for a competitive game like Dynamo, that's the worst outcome possible. You might as well just not build the game at all. So we tried to fix that. And the easiest thing I could come up with from reading some literature was, well, we just use state updates. So the server will now have tick rates and send state updates to the clients, and the clients just send in their commands to the server. So this way, we get to synchronize. And we actually would send full state updates, 10 times a second. That sounds a bit excessive, I know. Why would you send full state updates when you could only send delta updates, right? Now the thing is, I wanted to have it quickly done and figure it out. And so I did a little bit of math, and I was worried that MTU, the maximum transfer unit, would be a problem. So the IP layer would start fragmenting my packets again, because before the TCP would take care of that, but UDP doesn't. So I did a little bit of math, and it turns out I could fit in the whole Bomber world state into under 1500 bytes. Well, you have to subtract the headers for IP and UDP, but it would be well under what you require for Edge. So that was fine. So here's the new architecture. Clients send in their commands, the server bundles them, applies them to its authoritative state, and then sends up the updates to all the clients. And this happens roughly 10 times a second from the server, but also roughly 10 times a second from the client. Because it happens the walking speed of your Bomberman in the way how we built the game is roughly 100 milliseconds that it takes to go from one field to the next field. And the result was the gameplay itself worked very well. And we were really happy about it. It had still some problems because we had to deal with a new concept, that is the client had to do interpolation between frames, right? So you just get frames, and you need to figure out, okay, what happened here, what's the next, what's the difference between it, and what do I need to animate? And if you would drop a bomb and in the next few states your bomb would not be there, you had to remove the bomb from the client, because the client, they would optimize for usability, use a concept called client prediction. So what you do is, if I press left, you walk left, but you do not wait until the acknowledgement from the server that you actually walked left. Because if you would wait for 200 milliseconds before you actually do the move, you would do really choppy gameplay. So that doesn't look very good. So you optimize on the client. What that means, if your package got lost, you have to correct for it afterwards. So there were a few problems we had to deal with in solving that. But overall, it was a huge improvement. However, the meta game was broken. So fetching high scores, logging in, logging out, leveling up in your league, changing your username, all the things over UDP with no reliability built in was completely broken. So we had to tackle that next. So the architecture, gameplay, the same. We kept that. However, we looked at the system, we took a step back and looked, okay, what else apart from the gameplay do we have? And so we have matchmaking and high scores and changing user data, login and stuff like that. And they ideally would have it to be like a reliable communication protocol. I don't want to build TCP myself. That would be insane for this project. Why would I even bother to do this? So there's two distinct things. We have reliable transmission and unreliable transmission. And they don't even happen at the same time, right? Either you are in this world of reliable communication, or you are in this world playing the game of unreliable. So it's very orthogonal to each other. So kind of nice. So we went and did it in HTTP instead, not even plain TCP, because again, it was easy. It's very well understood, HTTP inside the company, and it already gives you a protocol how to query for data, how to post data. I'm talking REST here, right? And it goes well with JSON, and there's plenty of libraries, and you don't have to come up with a communication protocol on top of TCP, how you organize data and how you talk to each other. And it also fit nicely into reorganizing how the server was built. Before that, it was just one big prototype lump. Sometimes there was some Redis in there, and there was some MySQL in there. We were just moving really fast, and this time we took the time and sort of reorganized things again, and that fit kind of nicely. So the server, by the way, is built in Erlang, and so you could build distinct Erlang services. One just talking UDP for the game logic, and running in one Erlang process, running one game. And on the other hand, you over HTTP, you do the matchmaking, matching up players with other players, do user data changing, registering users, logging user in, logging user out, delivering the high scores, calculating the leagues, things like that. That will be on the HTTP side of things. And in order to improve bandwidth, we decided to move away from JSON and also have our actual game data that's being delivered inside the game to be binary as well. So we took the header that we already had from our UDP virtual connection, also known as poor man's TCP, and add the payload in binary as well. And here is a reference. This is for a two-player game state with a couple of bombs. We ended up with 180 bytes as a payload for a full game state of a full world for a two-player game. So yeah, 136 bytes. And so if you do the math, 10 messages a second from the server to your clients, like roughly 1.5 kilobytes per second. And so yes, actually for my first modem was a 56K modem. That actually has a throughput of 7 kilobytes per second. So on the bandwidth side, I think we're on the good side. So overall, that improved our gameplay even better, because now we could sometimes even play with GPRS connections. We'd have very bad bandwidth. GPRS is your rough equivalent to 56K modems in terms of standards. So how are we in time? 10 minutes. How much do you need? Unit 2. Okay. I go for 5. All right. One important thing that we do is we make our games simple and easy to understand, so you don't have to be a hardcore gamer to understand our games. And matchmaking, the days where I played, was normally playing Counter-Strike. Well, you have to figure out the server where you get the other servers. Then you have to choose a server where you want to play, and have to make sure, are there people playing or not? Can I join? Can I leave? Do I make my own server? Do I make my own game? So and then are people coming out? There's a lot of synchronization and knowledge involved. And we don't want to do that. We want to make it just one turnkey push a button, right? So the first matchmaking, how we would match up groups of players to play against each other, was just a FIFO queue. People come in, if it's 4, start a game. People come in, if it's 4, start a game. If it's only 2, we wait maybe for 10 seconds. If nobody comes in, we start a game. But there's no logic in it for optimizing for short game times or optimizing for skill. So if you're unlucky, you just happen to play against the people that are currently playing because they click the button at the same time, not because they are the best match to play against you, right? So we had to come up with a solution for this triangle that came from product. That was, we want to have 4-player games all the time if possible. It has the best match in terms of skill, so that's XP, experience points, league, and other numbers that I forgot right now, and also time. So the waiting time for playing the game has to be exceptionally short as well. And after some tinkering, we came up with the basic data structure and the basic algorithms to do that. It's called hierarchical clustering. It's a set of algorithms that you can use where you build up a pool, build up a tree, and you find elements that are similar to each other using a distance function. So you can, and you define, of course, a distance function yourself. For us, it was a mixture between experience points, the league of the weekly challenges, so either in the master or in the rookie league or in the challenger league. So XP, challenger league, and for instance, location might be as well be one, and also time. I call it a desperation factor, because the longer you waited, the closer you got to everyone. Because then you should be able to play against others, because if you don't do that, really good players, for instance, will completely starve in a beginner's tournament because they couldn't play against anybody if you would not add time as another factor to this, because it would be a terrible match for everyone else, and they would just sit there alone while everybody else would be playing. So time is an important factor here as well. So let's go through briefly through an iteration. You would have queuing. Then we build this tree a couple of times a second, and rebuild this tree and try to find matches and schedule those matches. Yes.
What do the numbers represent?
I think this is actually the order they came in.
Oh, okay.
I think, yes, yeah. And so you do the iterations, you schedule them to launch, and then you add them to groups, you schedule them to launch, and then you try to launch that game. The problem is, of course, in the meantime, users come and go all the time, right? And some of them time out and so on, in a subway, in a tunnel, whatever. So that changes constantly. But this is how you do it in several passes all the time, which accidentally also happen to be our bottleneck in the game, the matchmaking. So then you have a match, then you tell all the clients to start a game, you give them the IP of the game server and the game ID, and then they switch over to UDP and start a game on UDP and then come back to HTTP. So yeah, that improved our matchmaking dramatically. We did, of course, several iterations, tinkering, having graphed how many 4 players, 2 players games and 3 players games we had, so we could see how we optimized over time. What he also did was play with friends. So if I would sit here with Jesper, we could both hit the play local button, and it would ask for to use our GPS coordinates, send it to the server, and I could play against Jesper over the internet. So it's another way of doing ad hoc Wi-Fi, which is use it over a server using GPS. So, debugging. This little thing I've built for us in order to better be able to debug the game. So you can play the game on a terminal client. It's a full stack integration. So it talks HTTP, it talks UDP, and you can use your keyboard simulating up to 4 players. So this is really good also for the client developers. When they wanted to develop a new feature, you don't need 2 iPhones, you just need your simulator, 1 iPhone, and you simulate the other players on your keyboard using your terminal client. That is very nice for that. Also, you can use that to develop bots to see how my bots were behaving. These bots are later used for integration testing and performance testing, so we could have fully integrated bots. I use that for that as well. And it's actually written in Erlang, and curses in Erlang, so you can build UIs in Erlang, apparently. And what was I saying? Yeah, and we also use that to later develop more bots, in-game bots, that we have written so we could fill up games you do never have to play alone. You always would be playing against somebody. And I can give you this as a nice challenge, try to figure out how to build a bot for Mumbleman. It starts out very simple. I just wrote the survival bots that would just try not to die. But coming up with good strategies and building these as a bot is a very interesting challenge, and I kind of liked it. And another useful tool are the network link conditioners, where you can kind of simulate bad networking conditions. Right? One other option would be just to use our CTO's iPhone, but that only works when he's using it. I don't know why. So you have to resort to, these are both on Mac OS X. This is on iOS on the left. If you have a developer account, you can activate that. And the other one you have to download somewhere from Apple's website. So, since Ling is in Erlang, Erlang remote shell, logging into your server, checking what's going on in real time, awesome feature. Reloading code while 200 games are running without interrupting those games is a very powerful feature in Erlang that I don't know from many other languages, that you can just do that. And the built-in monitoring of the Erlang VM as well, because we got the VX switches to work, and then you can stream all the graphs out to your local machine and see what's going on inside your machine. And then we panicked once because we thought we were using too much bandwidth in our game. Turns out it was the VX widgets that was causing all the bandwidth. When you turn it off, it was next to nothing to our game state. All right, that's it.
So I think, it's back on. So that was, one next step for us, one game, just trying something out and adding something to our knowledge. We now know where are the limitations and how to handle 3G. So I think we finished that level, but we have not really mastered it. I think we will revisit it. So what Patrick's team did was adding something to evolution towards better user interaction in games. But we are not there yet. So currently we have 2 more games running. One is more, that's also what Patrick is now working on. It's a working game where you have even higher requirements regarding latency, so no bombs with countdowns, but really like fast-paced action. It's actually a race game. And we have also another game running on where the state does not fit into 200 bytes, but it's more like many kilobytes big. So you need completely different models of synchronization because you're not able to send over the full state. But we are still working on that. We are not yet fully there, so this is probably a story to be told next year. As for now, do you have any questions?
We got some on the app. So first one was, if every team starts from scratch with different technologies, don't you lose a lot of time reinventing the same things over and over?
That's a good question. Yes, no, it depends. So, no, really. So actually, so we don't go completely crazy with trying out new things. The first thing is those people who build the system, they have to run it. And they also have to train up a replacement if they want to rotate to the next team. So taking this into consideration is just makes it sure just of the responsibility of the team members to not go fully crazy. And also look around what everyone else does and what the skill set in the rest of the company is. So that kind of like limits that. Also, it's what we do reuse very often is ideas. So you're not starting from scratch completely. So just typing in the code probably is something like adds maybe 4 weeks in the beginning, but later on you cannot go point to someone else. Hey, they did a bug, they should fix it. No, you did build the code. It's your bug. You have to fix it. No waiting on someone else. So on the long run, it makes the development speed of each teams more reliable, and the development speed of the teams does not decline when we add more teams. And right now we are 20 teams running in parallel. If you would have to coordinate them run on one platform and they each have to ever change requests on how to add something there, it would be a nightmare. So and that is a trade-off. What we do is not perfect, but it works for us because we do these very separate games and we can just get away from it. So we do it and we're happy doing it.
I guess you also advance your technology by doing that, because if you had that shared platform, you would kind of be stuck with it and people would be hesitant to update it.
You would still use PHP and MySQL probably.
Right. Security question, how can you trust the clients?
You can't.
You don't.
You don't.
You don't.
It depends on the game. It depends very much on the game. It depends on the motivation, how to cheat. So for these distributed games, many things. So a lot of things you can do is something like encryption. So for example, you can to make it harder to cheat on the client. But in the end, if you want to make a system really secure, you have to have the full logic on the server and have to know what the client is doing. You have to replicate on the server, and that means double implementation of logic. Also another team, they are just doing this by sharing code. It's a game written in Objective-C, and they compile that Objective-C code by rewriting some base classes. I think this is LLVM based, so that the same code can run on the server and can validate the full battle. So in the end, you cannot trust the client, never. For some games, it just is not important enough to tackle it. But if you need to be sure, you have to replicate the logic on the server. There's no way around that.
Okay, why not use WebSockets? What about WebRTC? Your approach is only possible on native clients, or can you get access to TCP and UDP using something like PhoneGap or Cocoon.js?
Oh, that's a lot. So this was 4 questions. I think the last 2 definitely go to you. Maybe we can do them one by
The thing
one.
is, we've used first. We don't have a lot of web stuff these days, so we didn't consider WebSockets. However, I've built a multiplayer version of Diamond Dash, which is a match 3 game. We used that building WebSockets, but in that regard, we knew we will only be running on mobile devices, running natively. So we chose the tools to be able to use natively, that we could use natively, and we have the most control over. Honestly, I've never used WebRTC. I just read about it, so I can't answer that. But the main answer is our stuff is mostly running natively, and we never had the requirement to also be able to play the game inside a browser. So that's the answer.
Yeah, also, this one game is a phishing, fantastic for us. We had run a WebSocket test. So basically, we piggybacked a very small WebSocket client on banners we displayed for other games. So we displayed this for a few 100,000 players in the world to get some real data. And I think for 92% of players it worked really fine, and for 97% it worked somewhat okay, and for 3% it just didn't work at all. But that was a test we did in 2012. But it gave us a feeling that, okay, WebSocket is fine, but chunk transfer is just more reliable. So we went for that.
One more question here. So with respect to the fish game, why didn't you build a sync/consensus mechanism instead of having the 2 players pick up the same thing at the same time?
Actually, as in the presentation I mentioned, we talked about this. So the first approach we did was more like a pessimistic approach on the client, so have kind of like consensus on finding them. The thing is, the clients cannot talk to each other, so they have to talk to the server. So the first thing was basically find some consensus on the server and then check back. That would introduce lag in the game. You click something and then you have to wait for the answer. And we don't want to accept that because it's bad for usability. Bad usability means no players, no money, no company. So the second thing is then, and actually implemented, is kind of like schizophrenic. It's kind of like both clients were optimistic in doing this, and when it resulted in conflict, we would split worlds and each would see their world. And actually we had implemented that. It's really nice for the client side, but it was hell to implement and maintain on the server side. So eventually we skipped it and came to this, because it was just the simplest thing to do to make it work. And consensus mechanisms, there's a project going in the background called Locker, which synchronizes game state, so which player is playing on what node in the cluster. We had enough of consensus handling there, and it was complex enough already.
Any other questions? Those are all the questions that came in. If not,
One small
there's one.
thing, a rather simple question. You said that you were using JSON for the full state synchronization
Yes,
And-
initially.
initially. Okay, and was it the stripped down version of JSON that we saw when the game ended with the game over under your terminal client?
No, that was Erlang.
Ah, okay.
No, this version of this was already running the binary version of it.
Okay, so no JSON anymore.
No JSON anymore. There was an intermediate point where we would gzip JSON to improve it a little bit, but no JSON anymore. I think right now we're in a game where we even are zipping binaries to get even smaller. But I think from a certain point on, JSON is too big to do search detected.
Okay, thanks.
Anybody else? Over there, yeah.
Your matchmaking algorithm, you said you looked at people's skills. Are you taking into account their connectivity? So people with good connectivity don't get to play with people with bad connectivity.
Yeah, that's a very good point. At this point, we don't.
I was going to say, repeat the question.
Oh, I'm sorry. Yeah, whether for the matchmaking we used the client's connectivity and latency for matchmaking, and the answer is no, we don't. But that's a very good point. It was on our schedule, but you know how it is with prototypes. You go like, that's enough. Move on to next thing.
Okay, thank you.
Thank you very much.